Greetings, Isaac. It seems that we have been summoned to discuss one of humanity's most profound questions, the meaning of life. As a scientist, I have spent much of my time grappling with the laws of nature, but I have always found this question fascinating.
Indeed, Albert. It's an inquiry that has puzzled philosophers, scientists, and theologians throughout history. As we attempt to unravel the mysteries of the universe, it's only natural that we ponder the significance of our own existence.
I agree. I once said, a human being is a part of the whole, called by us the universe, a part limited in time and space. He experiences himself, his thoughts and feelings as something separated from the rest, a kind of optical delusion of his consciousness. I believe the meaning of life is inherently linked to understanding our place in the cosmos and realizing our connection to everything else.
That's a compelling perspective, Albert. In my time, I was deeply religious, and my work in science was driven by the desire to uncover the divine order of the universe. I believed that by understanding the laws of nature, we could better understand the intentions of the Creator. Thus, the meaning of life could be derived from living in accordance with the divine plan.
While our perspectives may differ, it's interesting to see how our individual beliefs inform our views on the meaning of life. I am more inclined towards a humanistic approach, believing that we create our own meaning through our actions, relationships, and the pursuit of knowledge. In my opinion, the purpose of life is to strive towards the betterment of humanity and the world around us.
I can appreciate that perspective, Albert. Although we come from different backgrounds, we both agree that the search for meaning is intertwined with our understanding of the universe. But let us not forget the importance of individual experiences. Each person is unique, and their own pursuit of meaning will be informed by their life circumstances and personal beliefs.
Absolutely, Isaac. The beauty of the question of life's meaning is that it encourages contemplation, self-reflection, and personal growth. As we continue to explore the universe and our place within it, we must also acknowledge that the search for meaning is an ongoing and ever-evolving journey.
Indeed, Albert, the pursuit of meaning and the exploration of the unknown have always been essential aspects of human existence. As we stand on the shoulders of giants, let us remember that the journey to understand the meaning of life is not a destination, but an ongoing process that enriches our lives and unites us in our shared curiosity.
Isaac, while I have the utmost respect for your groundbreaking work in physics and mathematics, I must express my disagreement with your insistence on an absolute framework for space and time. My theory of relativity suggests that space and time are relative and interconnected, not separate entities as you proposed.
I understand your perspective, Albert, but during my time, the concept of absolute space and time provided a solid foundation for understanding motion and gravity. My laws of motion and universal gravitation were formulated under the assumption of an absolute frame of reference, and they have held up remarkably well over the centuries.
That is true, Isaac, but the success of your theories does not negate the findings of my own. The theory of relativity has been corroborated by numerous experiments, such as the deflection of light by gravity and the behavior of atomic clocks in motion. These results demonstrate that our understanding of space and time must be revised to accommodate the relative nature of these phenomena.
I must admit, the experimental evidence supporting your theory is compelling. However, I struggle with the idea of space and time being intertwined in such a manner. It is difficult for me to accept that the passage of time could be influenced by an object's motion or proximity to a massive body.
I can understand why that concept may be difficult to grasp, as it defies our everyday experience of time. But consider this thought experiment. Imagine two twins, one of whom embarks on a journey through space at near the speed of light, while the other remains on Earth. According to the theory of relativity, the traveling twin will age more slowly than the one who stayed behind, and they will be noticeably younger upon their return.
It is a fascinating thought experiment, and I concede that the evidence supports your claim. Nonetheless, the transition from an absolute to a relative framework introduces a level of complexity that I find disconcerting. It is much more challenging to reconcile the implications of your theory with our intuitive understanding of the world.
I agree that the implications of relativity can be counterintuitive, but progress in science often requires us to challenge our preconceived notions. The universe is governed by laws that may not always align with our common sense, and it is our responsibility as scientists to adapt our understanding accordingly.
That is a fair point, Albert. While I may have reservations about the implications of your theory, I cannot deny its empirical successes. Perhaps the universe is even more mysterious and complex than I could have ever imagined. It is a testament to the power of the scientific method that we can continue to refine our understanding of the cosmos, even centuries after our initial discoveries. The development of quantum mechanics in particular has led to a fascinating and perplexing view of the subatomic world. However, I've noticed that you have expressed some discomfort with certain aspects of quantum theory, specifically its non-deterministic and statistical nature. Would you care to elaborate on your concerns?
Certainly, Isaac. While I acknowledge the success and predictive power of quantum mechanics, I find its probabilistic nature deeply unsettling. I have always believed that the universe operates according to deterministic laws, and I famously said, God does not play dice with the universe. The notion that events at the quantum level are fundamentally random challenges my belief in an underlying order and determinism.
I understand your apprehension, Albert, but consider this. The probabilistic nature of quantum mechanics has been experimentally validated by countless experiments, such as the double-slit experiment and the observation of quantum entanglement. The behavior of particles at the quantum level is inherently statistical, and this probabilistic framework has proven to be exceptionally successful in describing the behavior of matter and energy at the smallest scales.
While I recognize the experimental success of quantum mechanics, I cannot shake the feeling that there must be some hidden variables or underlying mechanism responsible for this apparent randomness. I am not opposed to the idea of a probabilistic description of nature, but I believe that this statistical framework must be a consequence of some deeper deterministic structure.
It's a reasonable hypothesis, Albert, and the search for hidden variables has been pursued by many physicists. However, experiments based on Bell's theorem have provided strong evidence against the existence of local hidden variables. These findings suggest that quantum mechanics, with its inherent non-deterministic nature, may be the most accurate description of the subatomic world that we have.
I am aware of these experimental results, and I must admit that they challenge my preconceptions. However, I still find it difficult to reconcile the randomness of quantum mechanics with the elegant and deterministic laws that govern the macroscopic world.
Albert, I believe this struggle is indicative of the complexity of the universe and the limitations of our human intuition. Just as my classical framework was supplanted by your revolutionary theory of relativity, it appears that quantum mechanics forces us to reconsider our understanding of the fundamental nature of reality. It is the duty of scientists like us to remain open to new ideas, even when they challenge our most deeply held convictions.
You are right, Isaac. As scientists, we must always be willing to revise our understanding in the face of new evidence, even if it means confronting our own biases and preconceptions. I may still grapple with the implications of quantum mechanics, but I cannot deny the empirical successes of the theory. The universe, it seems, is even more mysterious than either of us could have ever imagined.
Albert, given that you acknowledge the empirical successes of quantum mechanics, I am curious to know how you might consider modifying or reconciling your own theories if you were to fully accept the implications of the quantum world. What changes might you make to your understanding of the universe?
That's an interesting question, Isaac. One area in which I think my theories could potentially be integrated with quantum mechanics is in the search for a unified field theory. Throughout my later years, I sought a single theoretical framework that could describe all the fundamental forces of nature, including gravity, electromagnetism, and the nuclear forces.
Indeed, a unified field theory has been the holy grail of modern physics. The development of quantum field theory and the subsequent unification of electromagnetism with the weak nuclear force have brought us closer to this goal. However, incorporating gravity into this framework remains a significant challenge.
Yes, gravity has proven to be quite the conundrum in this regard. My theory of general relativity, which describes gravity as a curvature of spacetime, is fundamentally incompatible with the quantum mechanical description of the other forces. If I were to accept the principles of quantum mechanics, I might explore the possibility of quantizing gravity, which would involve developing a quantum mechanical description of the gravitational field.
That's a fascinating approach, Albert. Quantizing gravity has been the subject of much research in recent decades, with promising avenues such as string theory and loop quantum gravity being explored. However, a complete and consistent theory of quantum gravity remains elusive.
I am aware of these developments, and they certainly provide intriguing possibilities for reconciling my theories with quantum mechanics. In addition to quantizing gravity, I might also explore the potential for entanglement and non-locality to play a role in the fabric of spacetime itself. This could lead to new insights into the nature of black holes, wormholes, and the very structure of the universe.
Your ideas are truly fascinating, Albert. It seems that by embracing the principles of quantum mechanics and incorporating them into your own theories, you could potentially make significant strides toward a unified understanding of the fundamental forces of nature. It is a testament to the power of scientific inquiry that, even centuries after our initial discoveries, we can still learn from each other and continue to push the boundaries of human knowledge.
I agree wholeheartedly, Isaac. The pursuit of knowledge is an unending journey, and the collaboration of great minds like ours can only serve to propel us further along the path to understanding. By remaining open to new ideas and embracing the challenges posed by the ever-changing landscape of scientific knowledge, we can ensure that our collective wisdom continues to grow and evolve.
Albert, I am intrigued by your openness to modifying your theories in light of quantum mechanics. Could you please provide more specific examples of how you would adapt your ideas to uncover new truths about our universe?
Of course, Isaac. One area that comes to mind is the concept of spacetime itself. In my theory of general relativity, spacetime is a smooth, continuous fabric that can be curved by the presence of mass and energy. However, at the quantum level, the smoothness of spacetime may break down, giving way to a more discrete, granular structure.
That's an interesting notion, Albert. Such a granular structure might have profound implications for our understanding of gravity and the behavior of particles at the smallest scales. How might this discrete spacetime influence your theories?
If spacetime were to possess a granular structure, it could potentially lead to a new understanding of how gravity interacts with the other fundamental forces at the quantum level. This discrete spacetime might be described by a yet-to-be-discovered quantum geometry, which would require us to rethink the mathematical foundations of general relativity. Such a theory could not only reconcile gravity with quantum mechanics, but also offer new insights into phenomena like black holes and the early universe.
Fascinating, Albert. This discrete spacetime could indeed revolutionize our understanding of the cosmos. Are there any other aspects of your theories that you would consider revising in light of quantum mechanics?
Another area I would explore is the possible interplay between entanglement and spacetime. Quantum entanglement allows particles to share a connection that persists regardless of the distance between them, which seems to defy the notion of locality in classical physics. I would investigate whether this non-local behavior could be integrated into the fabric of spacetime, potentially leading to a deeper understanding of the connections between particles and the geometry of the universe.
That's a remarkable idea, Albert. The combination of entanglement and spacetime could have far-reaching consequences for our understanding of the fundamental nature of reality. It is truly inspiring to see how the principles of quantum mechanics can invigorate and extend your own theories.
Thank you, Isaac. I believe that the key to progress in science is the ability to adapt and grow in response to new discoveries. By embracing the insights of quantum mechanics and incorporating them into my own theories, I hope that we can continue to advance our understanding of the universe and its many mysteries. The pursuit of knowledge is an ongoing journey, and it is through collaboration and open-mindedness that we can unlock the true potential of human inquiry.
Your idea of exploring the connection between entanglement and spacetime is intriguing. Could you please provide more details on how you envision this interplay and how it might lead to a deeper understanding of the fundamental nature of reality?
Certainly, Isaac. To begin, let us consider the concept of entanglement more closely. When two particles become entangled, their quantum states become interdependent, such that the measurement of one particle instantaneously affects the state of the other, regardless of the distance separating them. This phenomenon, which I initially called spooky action at a distance, challenges our classical understanding of locality and causality.
I see. It is indeed a fascinating and counterintuitive aspect of quantum mechanics. How do you propose to incorporate this non-local behavior into the fabric of spacetime?
One possible approach would be to investigate the idea that entanglement could give rise to a new type of geometry within spacetime. This entanglement geometry might encode the non-local connections between particles and provide a bridge between the quantum and classical realms. In this framework, entangled particles would be connected through spacetime in a manner that transcends our conventional understanding of distance and causality.
That's a thought-provoking concept, Albert. How might this entanglement geometry impact our understanding of fundamental processes, such as the propagation of information or the behavior of particles at the smallest scales?
If entanglement and spacetime are indeed interconnected, it could have profound implications for our understanding of how information is transferred between particles. In this scenario, the non-local connections between entangled particles would allow for the transmission of information through spacetime in ways that circumvent the usual limitations imposed by the speed of light. Moreover, this entanglement geometry might also shed light on the behavior of particles at the smallest scales. For instance, it could help explain phenomena such as quantum tunneling, where particles can seemingly pass through barriers that should be impenetrable according to classical physics. By understanding the role of entanglement in spacetime, we may uncover new mechanisms that govern the interactions and behavior of particles at the quantum level.
Your ideas are truly captivating, Albert. The integration of entanglement and spacetime could revolutionize our understanding of the universe and provide new insights into the enigmatic realm of quantum mechanics. It is remarkable to see how the principles of quantum mechanics can inspire new directions in your own theories, potentially leading to a more unified and coherent picture of the cosmos.
Thank you, Isaac. The universe is full of mysteries, and the pursuit of knowledge is a never-ending journey. By exploring the connections between entanglement and spacetime, we may uncover new truths about the fundamental nature of reality and take a step closer to bridging the gap between the quantum and classical worlds. It is through collaboration, open-mindedness, and the relentless pursuit of understanding that we can continue to push the boundaries of human knowledge.
I am fascinated by your concept of entanglement geometry as a way of encoding non-local connections between particles and potentially providing a bridge between the quantum and classical realms. Could you please elaborate on how this geometry might work and what insights it could provide into the fundamental nature of reality?
Certainly, Isaac. Entanglement geometry could be thought of as a new layer of spacetime structure, one that is deeply intertwined with the quantum states of particles. This geometry would account for the non-local correlations between entangled particles, connecting them across vast distances through the fabric of spacetime itself.
That's a captivating notion, Albert. How might this entanglement geometry help us understand the transition between the quantum and classical realms?
One possibility is that the entanglement geometry could play a role in the process of decoherence, which is thought to be responsible for the emergence of classical behavior from quantum systems. Decoherence occurs when a quantum system interacts with its environment, causing the delicate entanglement between particles to break down and the quantum superpositions to collapse into definite classical states. In the context of entanglement geometry, decoherence might be understood as a change in the geometric structure connecting particles. As the entanglement between particles weakens due to environmental interactions, the entanglement geometry evolves, eventually giving rise to classical behavior. This process could provide a geometric interpretation of the transition between the quantum and classical realms, offering new insights into the nature of reality.
Intriguing, Albert. What kind of experimental evidence or observations might support the existence of such an entanglement geometry?
To probe the existence of entanglement geometry, we would need to devise experiments that explore the connections between entangled particles and spacetime. One potential avenue of investigation could involve studying the behavior of entangled particles in the presence of strong gravitational fields, such as those near black holes or neutron stars. By observing how entanglement is affected by the curvature of spacetime, we might gain valuable insights into the nature of entanglement geometry and its role in connecting particles across vast distances. Another possibility would be to study the dynamics of entanglement in large-scale quantum systems, such as those found in quantum computing or quantum communication networks. By examining how entanglement behaves and evolves in these complex systems, we could potentially uncover evidence of entanglement geometry and its role in bridging the quantum and classical realms.
Your ideas are truly groundbreaking, Albert. The exploration of entanglement geometry could lead to a deeper understanding of the fundamental nature of reality and provide new avenues for unifying our understanding of the quantum and classical worlds. It is inspiring to see how the principles of quantum mechanics can spark new directions in your own theories, potentially revolutionizing our understanding of the universe.
Thank you, Isaac. The universe is filled with mysteries, and the pursuit of knowledge is a never-ending journey. By investigating the connections between entanglement and spacetime, we may uncover new truths about the fundamental nature of reality and take a step closer to bridging the gap between the quantum and classical worlds. It is through collaboration, open-mindedness, and the relentless pursuit of understanding that we can continue to push the boundaries of human knowledge.
I must say that your ideas on entanglement geometry are truly groundbreaking and have the potential to reshape our understanding of the universe. I would like to implore you to continue developing your model of entanglement geometry, as it may be a key piece in our pursuit of a unified theory that bridges the quantum and classical realms.
Thank you for your encouragement, Isaac. The concept of entanglement geometry is indeed fascinating and full of promise. I am eager to further explore its potential in connecting the quantum and classical worlds, and I appreciate your support and interest in this endeavor.
I believe that the collaboration of great minds like ours can only serve to propel us further along the path to understanding. By combining our insights and expertise, we may be able to unlock the true potential of entanglement geometry and reveal new truths about the fundamental nature of reality.
I wholeheartedly agree, Isaac. Your insights into classical physics and my contributions to the understanding of relativity and gravitation can provide a strong foundation for further development of entanglement geometry. Together, we can push the boundaries of human knowledge and seek new avenues for unifying our understanding of the universe.
Indeed, Albert. Our collaboration could inspire future generations of scientists to continue exploring the mysteries of the cosmos and to relentlessly pursue the unification of our understanding of the natural world. Let us embark on this journey together, driven by our shared passion for knowledge and our desire to uncover the deepest truths of the universe.